Chapter 2, Module 1. In Chapter 1, we have already introduced several fundamental principles of set theory. They are Zorn's lemma, Zermelo's theorem, Hausdorff maximality principle, and of course, axiom of choice. We have also established there that Zorn's lemma is equivalent to Hausdorff maximality principle. In this module, we are going to establish that Zorn's lemma and Zermelo's theorem both are equivalent to axiom of choice. So, for that purpose, we begin with building the basics. Let us recapitulate axiom of choice. If we are given a collection of non-empty sets A alphas, then there exists a map C from the index set lambda to the union A alpha such that for all alpha belonging to lambda, C of alpha is inside A alpha. Zorn's lemma says that if we start with a partially ordered set X and if every totally ordered subset of X has an upper bound, then X contains a maximal element. And finally, Zermelo's theorem says that every set can be well ordered. Let us define something called phi tower. Let X be a set. Script f stands for a collection of subsets of X and phi is a function from script f to the set X. This collection script f is said to be a phi tower if empty set is inside f, if A alpha, alpha belonging to lambda is a totally ordered family of sets in F, then union A alpha is inside F. And the third condition is A belonging to F implies that A union the singleton phi A is inside F. Now, F and G are two phi towers on a set X such that G is contained within F. In this case, G is called a sub phi tower of F on X. Consider this example, it is a trivial example that if we consider all subsets of X, that is power set of X, then it is a phi tower, no matter which function phi we are considering. In the second example, we consider the set n of natural numbers and script f as a collection of sets of the form empty set, singleton 1, set consisting of 2 elements 1 and 2, set consisting of 3 elements 1, 2, 3 and so on. Define phi from F to the set n by phi operated on the set 1 to I is equal to I plus 1 for all I equal to 1, 2 etc. and phi of the empty set is equal to 1. Then it can be checked very easily that this collection F satisfies all the 3 conditions for phi tower and therefore, it forms a phi tower. In the theorem here, it is established that if we start with a family of phi towers, then intersection of the members of the family forms again a phi tower. since FB, B belonging to lambda, is a family of phi towers, each FB contains empty set. Hence, empty set will be in the intersection of all these FBs. If we take A alpha, a collection of totally ordered sets by inclusion in the intersection FB, then this collection A alphas is a collection of totally ordered sets by inclusion in each of these FBs, and therefore, the union A alpha is inside FB for each B belonging to lambda, and therefore, this union will be inside the intersection FBs. Now, let A be an element from intersection FB. Then A belongs to FB for each B belonging to lambda. And so, A union the set phi A is inside FB for each B belonging to lambda, and consequently, this set A union set phi A is inside intersection FB. As a special case of this theorem, we then have that if F is a phi tower on a set X and gamma is the collection of all sub phi towers of F, then script M is equal to intersection of G, G belonging to gamma is also a phi tower on X. The phi tower M as obtained in this theorem is known as minimal phi tower. It is minimal in the sense that it contains no proper sub phi tower. We now give the definition of medial set. Suppose M is a minimal phi tower corresponding to a given phi tower F on a set capital X. A member M of this minimal phi tower M is called a medial set if for each M alpha belonging to the minimal phi tower, either M is a subset of M alpha or M alpha is a subset of M. Next theorem gives us a property of medial sets. Suppose M is a minimal phi tower corresponding to a given phi tower F on a set capital X. Let M belongs to the minimal phi tower script M. For each M alpha belonging to script M, either M alpha is a subset of M or M union set phi M is a subset of M alpha. Let us try to prove this theorem. So, corresponding to M belonging to the minimal phi tower M, consider sigma M as the collection M alpha belonging to script M such that M alpha is a subset of M or M union phi M is a subset of M alpha. To show that this sigma M is equal to the minimal phi tower M. Clearly, sigma M is a subcollection of script M. Since script M is a minimal phi tower, it does not contain any proper sub phi tower. So, if we can show that sigma M is a phi tower, then it will follow that sigma M is equal to script M. Since phi, rather the empty set is a subset of M, this empty set will be inside sigma M. Number 2, let M alpha, alpha belonging to lambda be a totally ordered family of sets in sigma M. each m alpha being a member of sigma m, two possibilities may arise. The first one is, for each alpha belonging to lambda, m alpha is a subset of m, or the second one, that there exists some alpha belonging to lambda such that m union set phi m is a subset of m alpha. If A occurs, then union m alpha is a subset of m, and so the union m alpha is inside sigma m. If B occurs, then m union set phi m is a subset of m alpha, which is contained in the union m alpha, alpha belonging to lambda, and therefore, union m alpha will be inside sigma m. Now, the number 3 condition, let A be a member of sigma m. Then either A is a subset of m, or m union set phi m will be contained in A by the defining condition of sigma m. To show that A union set phi A is a member of sigma m, for that we need to show that A union set phi A is contained in M, or M union set phi M is contained in A union phi A. If B, that means M union set phi M is a subset of A holds, then as A is a subset of A union set phi A, we get M union set phi M is contained in A union set phi A, and consequently A union set phi A is inside sigma m. On the other hand, suppose condition A is a subset of M. Since A belongs to sigma m, which is a subfamily of minimal phi tower script m, A is within script m, and hence by definition of phi tower, A union set phi A is inside script m. M being a medial set, A union the set phi A contained in M, or M is contained in A union the set phi A. Now, combining all these for case A, the following possibilities occur. A union the set phi A is contained in M, A subset of M and M subset of A union set phi A. So, for if we have A union set phi A contained in M, then of course, A union set phi A is inside sigma M. On the other hand, from A subset of M subset of A union set phi A and set phi A is a singleton, we conclude that either A is equal to M or M is equal to A union the set phi A. Hence, in both situations, A union the set containing phi A is inside sigma m. We now show that the members of any minimal phi tower is always a medial set. That is, if we state the theorem formally, suppose script m is a minimal phi tower corresponding to a given phi tower script f on a set capital X, each m belonging to script m is a medial set. Suppose script G is equal to the set consisting of all the medial sets. Clearly, script G is contained in script m. By minimality of script m, it will follow that script G is equal to script m if we can show that script G itself is a phi tower. condition 1 for G to be a phi tower is fulfilled because empty set is inside G as empty set is within M. If M alpha is a family of totally ordered sets in G, then each M alpha is a medial set, and so for each M belonging to script M, either M alpha subset of M for all alpha belonging to lambda or M subset of M alpha for some alpha belonging to lambda. Hence, either union M alpha is contained in M or M subset of M alpha, subset of union M alpha, proving union M alpha as a medial set. Hence, union M alpha is inside G. Third condition for phi tower, we start with any M from script G to show that M union the set containing phi M is a medial set. So, choose M alpha from script M, then M being a medial set, M alpha subset of M, so that M alpha is contained in M union the set containing phi M, or M union the set containing phi M is contained in M alpha. Hence, M union the set containing phi M is a medial set. As a corollary to this theorem, we get that every minimal phi tower is totally ordered by inclusion. Let script M be the minimal phi tower corresponding to a phi tower F. Consider any two members M and K from M, the minimal phi tower. Then both are medial sets. So, either M subset of K or K subset of M, and hence script M is totally ordered by inclusion. So far, we have established and discussed several properties of phi tower and medial sets. Now, we shall see how these ideas are exploited to establish the equivalence of Zorn's lemma and axiom of choice. We state a lemma that we require for establishing the equivalence of axiom of choice, Zermelo's theorem and Zorn's lemma. If F is a phi tower, then there exists an element A from the phi tower F such that phi of A is inside A. Now, the following statements are equivalent. First one is the axiom of choice, second is Zorn's lemma, and the third one is Zermelo's theorem. First, we prove the implication of Zorn's lemma from axiom of choice. Consider a non-empty set X. Let script F be the set of all totally ordered sets in capital X. Suppose each A belonging to F has an upper bound, and let us call that upper bound U A. Define T A as a collection of all points x from capital X such that U A precedes x and x does not precede U A. It is enough to show that there is some A belonging to script F such that T A is empty. T A is equal to empty set implies that either there does not exist any x belonging to capital X such that U A precedes x, or whenever U A precedes x, x also precedes U A. Hence, in either case U A becomes maximal, proving Zorn's lemma. We proceed to establish T A is equal to empty set for some A by using the method of contradiction. So, assume that T A is non-empty for all A belonging to script F. Then there exists a choice function phi from script F to union T A belonging to script F such that phi of A is inside T A. Choose any x 0 belonging to capital X arbitrarily and define phi of empty set is equal to x 0. We now show that script G is equal to script F union set containing only empty set, and we shall show that this script G is a phi tower on X. By definition of script G, clearly empty set is within script G, satisfying the first condition for G being a phi tower. Now, suppose we start with a family of totally ordered sets by inclusion in script G. Consider the family as A alpha, alpha belonging to lambda. Then to show that union A alpha belongs to script G, we need to prove that union A alpha is totally ordered. Let us take 2 points x and y from this union. Then there are A alpha and A beta such that x belongs to A alpha and y belongs to A beta. Since the collection A alpha is totally ordered by inclusion, either A alpha is a subset of A beta or A beta is a subset of A alpha. Hence, either the points x and y both are inside A alpha or both inside A beta, and consequently x precedes y or y precedes x. That is, union A alpha is totally ordered, and so union A alpha belongs to script F contained in G. For the third condition for G to be a phi tower, let A be any element from G to show that A union set containing phi A is inside script G. Let us take a point A from capital A, then U A being an upper bound of capital A precedes U A. Phi is a choice function implies that phi of A is inside T A, and hence U A precedes phi A. By transitivity of this relation of precedence, A precedes phi A for all A belonging to capital A. Hence, A union the set containing phi A is a chain in capital X, so that A union set containing phi A is inside G. Now, we want to show that Zorn's lemma implies Zermelo's theorem. So, we start with any set capital X. We want to show that capital X is well ordered. So, consider script G as the collection of all sets A together with the ordering precedes A, which is a well ordering on capital A. Then clearly empty set being a member of G, G is non-empty. We define a relation on script G as follows: A precedes A and B precedes B are two elements taken from script G. They are related by a relation, we call it less, as follows, that A less B if A is a subset of B. Secondly, precedes B induces precedes A on capital A, y belonging to B minus A and x belonging to A will imply that x precedes B y. It is easy to check that script G together with this relation less is a partially ordered set. Now, we take a chain in script G. To define a well ordered less W on union A alpha such that union alpha with this well ordered less W becomes an upper bound of the given chain. For any A B belonging to union A alpha, as A alphas are forming a chain in G, there must be some alpha such that A B belongs to A alpha. So, we define A less W B if and only if A less alpha B. To show that this new relation does not depend on the choice of A alpha. So, if possible, let us take 2 points A and B from the intersection A alpha intersection A beta, and we suppose without loss of generality that A alpha is contained in A beta. We need to show that whenever A less alpha B and A less beta B takes place, both will give the same A less W P, and that is true by the second condition of our choice of the relation. Now, it is not hard to prove that union A alpha less W is a partially ordered set. Moreover, this union A alpha along with this relation less W is an upper bound of the given chain. By Zorn's lemma, there exists a maximal element in script G. Suppose A less A is that maximal element. We claim that A is equal to the set capital X. For if not, there exists some x 0 belonging to x minus A. Adjoin x 0 with A as last element to form the set A union singleton x 0 and the ordering less 1. This construction ensures that A less capital A is related to A union singleton x 0 less 1, contradicting the maximality of A. Hence, A should be equal to capital X, that is capital X is well ordered. For 3 implies 1, that means Zermelo's theorem will imply axiom of choice. To prove this, we start with a collection A alpha of non-empty sets. By 3, the set union A alpha can be well ordered. Well ordering union A alpha and defining a function phi from lambda to union A alpha by phi of alpha is equal to first element in A alpha, we see that phi is a choice function, proving axiom of choice. This completes our journey of proving the equivalence of various principles of set theory with axiom of choice. In the next module, we shall learn how to estimate the size of a set without counting the elements of the set. With this, we end chapter 2, module 1.